feeder should not be tapped for more than one appliance according to the National Electrical Code Section 424.3a. Heaters shall be supplied by individual branch circuits based on Section 422.11. Conductors should not be installed where they can be exposed to physical damage, Section 225.14. Building codes may not have been followed for enclosures because the hallway structure may not comply with building codes for enclosures. Water intrusion is a concern. The open sides of the hallway allow water to penetrate during rainfall, potentially damaging electrical equipment. The absence of lighting raises safety concerns for daytime use. I recommend you calculate the existing and proposed loads to determine if the panel has sufficient ampacity with a service calculation. Correct the number 6 wire feeder violation by installing number 4 wire per 424.3 for feeder sizing. Provide separate branch circuits for each heater. Replace the dual fuse switches with single pole switches as required by 422.11. Ensure the electrical equipment is properly enclosed to prevent water intrusion by using proper enclosures. Install lighting fixtures to provide adequate illumination for daytime use. If the service calculation indicates insufficient ampacity, consider upgrading the service. Obtain the necessary building permits for the hallway structure. Coordinate with the contractor to address building code and water intrusion concerns. Let's delve deeper into the specific electrical violations and recommended solutions for this hallway heater installation. Firstly, Section 424.3 of the National Electrical Code, or NEC, clearly states that feeders should not be tapped to supply more than one appliance. In the context of this installation, using a single feeder to supply multiple heaters violates this code. The intention of this rule is to prevent overloading the feeder, which could lead to overheating and potentially a fire hazard. The proposed solution involves installing a dedicated feeder for each heater, ensuring that each appliance has its own independent power source. This approach not only complies with the NEC but also enhances the overall safety and reliability of the electrical system. Secondly, Section 422.11 of the NEC mandates that heaters must be supplied by individual branch circuits. This means that each heater should have its own circuit breaker in the electrical panel, providing overcurrent protection specifically tailored to the heater's requirements. The violation in this case stems from the attempt to feed multiple heaters from a single branch circuit, which could overload the circuit and potentially damage the heaters or create a fire hazard. The solution is to install a separate branch circuit for each heater, with appropriately sized wiring and a circuit breaker that matches the heater's ampacity. This ensures that each heater receives the correct amount of power and that the circuit is adequately protected against overloads and short circuits. Thirdly, Section 225.14 of the NEC prohibits the installation of conductors in locations where they are exposed to physical damage. In this hallway installation, the wiring is run in a ENT conduit with set screw fittings, which may not provide adequate protection against physical damage, especially considering the open sides of the hallway and the potential for water intrusion. The code aims to protect the conductors from damage that could compromise their insulation and lead to electrical hazards. The recommendation is to ensure that the wiring is properly protected from physical damage by using appropriate conduit types and fittings that are suitable for the environment. This may involve using rigid metal conduit or liquid-tight flexible metal conduit to provide a more robust and weather-resistant enclosure for the conductors. In addition to these specific electrical violations, there are also several additional concerns that need to be addressed. One concern is the potential non-compliance with building codes for enclosures. The hallway structure itself, which is described as an awning with sides made of a 2x2 metal frame bolted to the sidewalk, may not meet the requirements for a permanent enclosure. Building codes typically specify minimum standards for structural integrity, fire resistance, and weather protection. It is essential to consult with a qualified building inspector to determine whether the hallway structure meets the applicable building codes. If it does not, modifications may be necessary to bring it into compliance. Another concern is water intrusion. The open sides of the hallway allow water to penetrate during rainfall, which could damage the electrical equipment and create a safety hazard. Water can corrode electrical connections, compromise insulation, and cause short circuits. To mitigate this risk, it is essential to ensure that all electrical equipment is properly enclosed in waterproof or weather-resistant enclosures. This includes the junction boxes, switches, and receptacles. Additionally, measures should be taken to prevent water from entering the hallway, such as installing gutters or awnings to divert rainwater away from the structure. The absence of lighting is another significant concern. The hallway is intended for daytime use for physical therapy, but even during the day, adequate lighting is necessary to ensure the safety and well-being of the users. Insufficient lighting can increase the risk of trips, falls, and other accidents. It is recommended to install lighting fixtures that provide adequate illumination throughout the hallway. The lighting should be designed to provide uniform and glare-free illumination, and it should be controlled by switches that are easily accessible to the users. Now, let's discuss the recommended solutions in more detail. Firstly, a service calculation is essential to determine whether the existing electrical panel has sufficient ampacity to handle the additional load of the heaters. A service calculation involves adding up all of the loads on the electrical system, including lighting, receptacles, appliances, and heating equipment. The total load is then compared to the ampacity of the main breaker in the electrical panel. If the total load exceeds the ampacity of the main breaker, the service is considered to be overloaded, and an upgrade is necessary. In this case, the addition of 8 3000-watt heaters represents a significant increase in the electrical load. It is highly likely that the existing panel will not have sufficient ampacity to handle this additional load, and a service upgrade will be required. Secondly, the number 6 wire feeder violation needs to be corrected by installing number 4 wire per 424.3A. The number 6 wire is not large enough to carry the current required by the heaters, and it is therefore undersized. Undersized wiring can overheat and cause a fire hazard. The number 4 wire is the correct size for the load, and it will provide adequate ampacity to safely power the heaters. Thirdly, separate branch circuits should be provided for each heater. This will ensure that each heater has its own independent overcurrent protection and that the circuit is not overloaded. Each branch circuit should be sized according to the heater's ampacity, and it should be protected by a circuit breaker that matches the circuit's ampacity. Fourthly, the dual fuse switches should be replaced with single pole switches as required by 422.11. Dual fuse switches are not typically used for heater circuits, and they may not provide adequate protection against overloads and short circuits. Single pole switches are the standard type of switch used for heater circuits, and they provide reliable on-off control. Fifthly, the electrical equipment should be properly enclosed to prevent water intrusion. This includes junction boxes, switches, and receptacles. All electrical equipment should be rated for the environment in which it is installed, and it should be installed in accordance with the manufacturer's instructions. Sixthly, lighting fixtures should be installed to provide adequate illumination for daytime use. The lighting should be designed to provide uniform and glare-free illumination, and it should be controlled by switches that are easily accessible to the users. In addition to these specific recommendations, there are also some additional considerations that should be taken into account. If the service calculation indicates insufficient ampacity, consider upgrading the service. A service upgrade involves replacing the existing electrical panel with a larger panel that has a higher ampacity. This will provide the necessary capacity to handle the additional load of the heaters. Obtain the necessary building permits for the hallway structure. Building permits are required for most types of construction and ensure that the work is done in accordance with the applicable building codes. Coordinate with the contractor to address building code and water intrusion concerns. The contractor should be responsible for ensuring that the hallway structure meets the applicable building codes and that measures are taken to prevent water intrusion. The importance of these corrective actions cannot be overstated. Firstly, safety is paramount. Addressing electrical violations, ensuring proper wiring, and preventing water intrusion minimizes the risk of electrical shocks, fires, and equipment damage, safeguarding the well-being of residents, staff, and visitors. Secondly, compliance with the National Electrical Code is not just a legal requirement but a fundamental principle of responsible electrical work. Adhering to the NEC ensures that electrical systems are installed and maintained to the highest safety standards. Thirdly, long-term reliability and cost-effectiveness are enhanced. Correcting the violations and implementing the recommended solutions can prevent future problems, reduce maintenance costs, and extend the lifespan of the electrical equipment. Failing to address these issues can lead to costly repairs, downtime, and potential liability. This comprehensive approach will bring the hallway heater installation into compliance with the National Electrical Code, enhance safety, and ensure the long-term reliability of the electrical system. Remember to consult with qualified professionals, including licensed electricians and building inspectors, to ensure that all work is performed safely and in accordance with all applicable codes and regulations. Electrical work can be dangerous, and it should only be performed by qualified individuals who have the necessary training and experience. The National Electrical Code is a complex document, and it is essential to have a thorough understanding of its requirements before undertaking any electrical work. By following these recommendations, you can create a safe and reliable electrical system that will serve the needs of the assisted living center for years to come. The proposed installation of 8 3000-watt 208-volt radiant heaters presents a significant electrical load. Let's examine the implications of this load and the necessary calculations to ensure the electrical system can handle it safely and effectively. Firstly, calculate the total heater load. 8 heaters, each drawing 3000 watts, results in a total load of 24,000 watts. This is a substantial amount of power that needs to be carefully considered in the context of the existing electrical system. Secondly, convert watts to amps. To determine the current draw, we use the formula amps equals watts divided by volts. In this case, 24,000 watts divided by 208 volts equals approximately 115.4 amps. This is the total current that the heaters would draw when operating simultaneously. Thirdly, consider the continuous load factor. Since the heaters are intended for continuous use, we need to apply a continuous load factor of 125% as required by the National Electrical Code. This means that the circuit must be capable of handling 125% of the total current draw. Applying this factor, 115.4 amps multiplied by 1.25 equals 144.3 amps. This is the minimum ampacity that the circuit must have to safely power the heaters. Fourthly, evaluate the panel capacity. The existing electrical panel has a 175 amp main breaker. However, it is crucial to determine how much of that capacity is already being used by existing loads. A service calculation is necessary to assess the existing load and determine the available capacity. The service calculation involves adding up all of the loads in the electrical system, including lighting, receptacles, appliances, and other equipment. The total load is then compared to the ampacity of the main breaker. If the existing load is already close to the 175 amp limit, adding the heater load could overload the panel and create a safety hazard. Fifthly, determine the required breaker size. Based on the continuous load calculation, the circuit must be capable of handling at least 144.3 amps. Therefore, the circuit breaker protecting the heater circuit must be rated for at least 150 amps. It is important to choose a breaker size that is appropriate for the wire size and the heater load. Sixthly, select the appropriate wire size. The wire size must be selected to handle the continuous load of 144.3 amps. According to the National Electrical Code Table 310.16, number 1 aluminum wire or number 1 or 0 copper wire is required to carry this amount of current. It is important to consult the NEC and local codes to determine the appropriate wire size for the specific installation conditions. Seventhly, address the proposed wiring violation. The proposal to feed the heaters with 260 amp breakers and number 6 wire violates the NEC. Number 6 wire is not large enough to handle the continuous load of the heaters, and it is also a violation of the rule that feeders should not be tapped to supply more than one appliance. Each heater must have its own dedicated branch circuit with the appropriate wire size and breaker protection. Eighthly, correct the tapping violation. The proposal to tap the number 6 wires with number 12 wires to feed a dual fuse switch is also a violation of the NEC. Tapping a smaller wire off of a larger wire is not permitted unless the smaller wire is protected by an overcurrent device that is sized appropriately for the smaller wire. In this case, the number 12 wire is not protected by an overcurrent device that is sized appropriately for the heater load. Ninthly, ensure proper overcurrent protection. Each heater must have its own dedicated overcurrent protection device, such as a circuit breaker or fuse. The overcurrent protection device must be sized appropriately for the heater load and the wire size. This will protect the circuit from overloads and short circuits. Tenthly, verify the voltage drop. Voltage drop is the decrease in voltage that occurs along a wire due to the resistance of the wire. Excessive voltage drop can cause the heaters to operate inefficiently and can even damage them. It is important to calculate the voltage drop to ensure that it is within acceptable limits. The NEC recommends that the voltage drop should not exceed 3% for branch circuits and 5% for feeders. The wire size should be increased if necessary to reduce the voltage drop. The existing electrical panel with a 175 amp main breaker is likely to be insufficient to handle the additional load of the 8 3000 watt heaters. A service upgrade will likely be required to provide the necessary capacity.